The two-dimensional heat equation is an equation for the heat conduction in a plate. And so what we have is a plate of dimensions a and b. Let's plot this here from 0 to a in x direction and from 0 to b in y direction. So then this would be y and this would be x. Now here's the heat equation in two dimensions. So we have a time derivative t and then we have x and y, which is the two-dimensional plate. Now, rule of thumb for boundary conditions. So here we have a time derivative, so we need an initial condition, which is here at the bottom. At time 0, we have f of x and y. And then we have two x and two y derivatives, so we need four side conditions. And we have four side conditions. One is, if x is 0, then the temperature is held at 0. So if x is 0, this is here on the left side. So here the temperature is 0. If x is a, which is the right end of the plate, then there is no flux. So here. And then we have, if y is equal to 0, which is here on the bottom, we have also no flux. And then if y is equal to b here on the top, we have no flux. Or we call them also homogeneous Neumann boundary conditions. So we have three sides with homogeneous Neumann boundary conditions, and only on the left side we have a fixed temperature of 0 degrees. So that's the problem we have to solve. Of course we use separation, but now we have three variables to worry about, so we call separation a function x of x, a function big Y of y, and a function t of t. So as many variables as we have, as many functions we are using. If we differentiate this by time, okay, the time is only in the t, then we only get a t prime, and x and y just become factors. If we differentiate with respect to x, this guy, okay, then we get an x double prime, and y and t are factors. And if we differentiate with respect to y, well, then we get a y double prime from the heat equation, and then x and t are factors. We have done this for the 1D heat equation, for the 2D heat equation, and then we worry about t, x, and y, so we need to be a bit careful. Nice. Now this one here, we divide by x times y times t. So what happens on the left-hand side? If I divide by x and y, okay, then these cancel, and we get a t prime divided by t, which is here. I also took care of the k, so the k factor goes then here, so I divide actually also by k. Let's put that here. Let's look at this factor now, x double prime yt. If I divide this by xyt, then I get x double prime divided by x right here. And now for this term, if I divide it by xyt, yeah, well, then I get y double prime divided by y. Okay, so now the left-hand side only depends on t. The right-hand side only depends on x and y. So meaning either side must be equal to a constant, so we introduce a constant of separation, and we call this minus lambda, as we did so many times before. But now we are not done, because the x and y equation is still coupled, right? So I can write, if I take the x and y part, I can write x double prime over x is minus lambda minus y double prime over y. Now the left-hand side only depends on x, and the right-hand side only on y. So we can do separation again. Isn't it crazy? So we do separation again. We get a second separation constant. We need a name, so we call it tau, or minus tau. So then all this has to be equal to minus tau. This is a new thing. We need to make sure we keep track of the first separation constant lambda and the second one tau. Okay, let's see how this works. Let's look at the boundary conditions. At 0 on the left boundary we have 0 temperature. This is a boundary condition for x. On the right boundary we have no flux, so this is an x prime at a is 0. And on the top of bottom, these are conditions for y. So y prime at 0 is y prime at b is equal to 0. These are no flux on the top. This is no flux on the bottom and on the top. So then we can combine them. From the x problem, we get the x spatial problem here. X double prime plus tau x is 0. X is between 0 and a, and then we have a mixed type of boundary conditions. Right, one is Dirichlet and one is Neumann. For the y problem right here, we have y double prime plus alpha y is 0, where alpha then is equal to lambda minus tau. Y prime at 0 is 0, y prime at b is 0, so here we have homogeneous Neumann conditions. So this means for the y problem, we know already the solutions, right? This will be cosine solutions, and the eigenvalues will be n pi divided by b all squared. Ha! And for the mixed type, actually, we know the solutions too. So let's come to that. Oh yeah, first, let's look at the time problem. So the time problem came from up here. I need to go back just a bit. So here, this is for the time problem. So we have t prime is equal to minus lambda kt. So this is then what I write down here. Okay, let's look at the x problem now. The x problem is of mixed type. I go back to our summary. Here we go. Here's the summary. We have one of these two mixed types. Actually, we have this one, right? We have Dirichlet at 0, and we have no flux or Neumann at L, but now L is called A. So then the eigenvalues are 2n minus 1 pi divided by 2L all squared. And the eigenfunctions are the sine with the same 2n minus 1 pi x divided by 2L. And now L is A, okay? And lambda, I think, is tau in our case. Wonderful. So let's use that. Back here, so then we use this. So the eigenvalues tau n, then I'll get an index n, are 2n minus 1 pi divided by 2a all squared. And the corresponding functions are the sine with the 2n minus 1 pi x divided by 2a. Awesome. For the y problem, homogeneous Neumann, we know it's cosine. So we can write this down right away here. So then the alphas, now we need to use a different index m because the index n has been used already in the previous problem. So we have m pi over b square, and the eigenfunctions are the cosine with an m pi y divided by b. Notice also this depends on y, so we put a y here. Right, this depended on x, so we put an x there. And here's the index n, and here's the index m. So what we do get is we get two sets of indices, n and m. Let's see what this does to the lambda. Lambda was from earlier tau plus alpha. But now the tau gets the index n, the alpha gets the index m. So then the lambda gets two indices, n and m. And so the tau n's were these, and the alpha m's were those. And so now we have two indices, n and m. N goes from 1 and 2 and 3 and so on. M goes from 0 to 1 and 2 and 3 and so on. Isn't that crazy? You get a separation constant which depends on two indices. Wonderful. For the time problem, it means that this actually shows up right here in the exponential for the time problem solution. So then t also gets two indices, n and m. Here's a wonderful spot to get confused or to get lost. It is really important, if you get a new index, you give it a new name, that you don't mix them up. Okay, so then coming back to the separation, then the x had the index n, the y, we introduced a new index m, the t got all of a sudden two indices, n and m, and so then our general solution has also two indices, and we get the eigenfunction for x, we get the eigenfunction for y, and we get the time component, which is an exponential. So, okay, and then we can write this as a fancy series. So we need coefficients which have two indices. We have the xn functions, the yn functions, the time function, and we sum up over all possible indices. Now for the initial condition, let's in sub n t is 0, which happens only here. E to the 0 is 1. So we get the whole series, but just without the exponential term. So this happens here. So the initial condition is given by the sum over n and m, coefficients c and m, sine of 2n minus 1 pi x over 2a times cosine of m pi y over b. So how do we find the c and m? Now comes a cool trick by flipping the order of these terms here, and then noticing that the inner sum, m is 0 to infinity, c and m cosine m pi y over b, this can be understood to be a function of y, which only depends on the index n, because the index m has been summed over. So then what this is, really, is just a sine series of f, right? It is a sine series with the arguments 2n minus 1 pi x divided by 2a, where the bn now are the sine series coefficients. Okay, but we know how to compute those. Where is this? Here. We know the coefficients of a Fourier sine series can be computed exactly as written here, right? So the f gets there, is integrated with the sine 2n minus 1 pi x divided by 2a. Whatever that is, divided by times 2 over a, then will be the coefficient bn. Okay, but earlier, so we defined bn to be the sum. So now we can also compute the cnm, because this is a standard cosine series. Okay, it's a cosine series of bn of y. So then we have two cases. We have the index 0. That was always special, right? So this is then 1 over b integral 0 to b bn of y. And bn of y can be just subbed in, which is actually this term. So this will be the coefficient cn0. For cnm, we integrate bn with the cosine, because it's a cosine series coefficient. We sub in the bnm, which was this bit here, and then we get the coefficient cnm. This looks rather complicated, and you bet it is. So if we know f, you have to put the f in here, the initial condition. You have to solve this double integral with the sine and the cosine for all combinations of n and m to get all your coefficients c and m. Make no mistakes, this is quite some math to be done. But then if you have them, and you're done. You have a beautiful solution. One more afterthought here. As t goes to infinity, let's just look at this for very quickly. As t goes to infinity, the t arises here in the exponent, and the lambdas are all positive, so with a minus sign, we get e to the minus something t, which goes to 0. So all the exponential terms go to 0, which means the entire series goes to 0. So the limit, as t goes to infinity, is 0. So meaning the entire plate, which had 0 degrees here, and no flux, so insulated sides here and here and here, will eventually reach 0 degrees just everywhere. To summarize, so the key idea happens right here, where you get two separation constants, lambda and tau, and then you combine them in another constant, alpha, as lambda minus tau.